Hello, everyone. Good afternoon. Welcome to another video lecture, or actually Zoom session for ComSci 191 operating systems, cybersecurity, and ito ay continuation lang basically nung diniscuss natin about cryptography last time. So there were 3 students who attended last time. Pero ngayon, i-discuss natin yung part 2, which is on the public key cryptography. Okay, so in this session, we're going to look at public key cryptography. Right, one of the questions that one of the solutions to achieve confidentiality is through encryption, as we discussed last time. Now, how do we protect against things like falsification? So, meaning, how do you know that a particular data or file is authentic? So, it's better that if we have some techniques to do that. So the first one is, what do we mean when we say authentic? Right? So this means that the contents are unaltered. Which means if you downloaded a file and you think that, let's say, that file is authentic, then the contents of that file were not modified in some form or another. For example, if you have a program or a picture, etc. So the contents are unaltered. The second one is, it came from a legitimate source. How do you verify that this file really came from this particular source? Right? For example, if you're installing packages, how do you know that that package was developed by Microsoft or some other companies? So that's the second one. And the third one is timely and in correct sequence. So there are some types of applications or programs that the timing is important. So it should be able to determine that the order or the sequence is correct. So there should be some way or some mechanisms to achieve this authenticity, or to verify the authenticity of certain things that we get from the internet. Now, the question for the recitation, since walang umattend, okay, so can we use encryption to achieve this? Yes, we can use encryption to achieve this authenticity, because remember that last time when we talked about secret key encryption, it is the sender and the receiver should both know the key, right? So if they both know the key, then it's possible, or it's sure that the sender can encrypt and the receiver can decrypt, then the contents are authentic. Right? So we can use encryption for this. However, there are some applications wherein encryption is not sufficient or inefficient when we're trying to achieve authenticity. Okay, so we talked about last time hashing. Right? So we talked about hashing, and basically it's synonymous, or it's the same as hash function. So hashing, as discussed last time. So the idea is you have a message M, and then you pass it to a hash function, right, H, and you get a fixed length hash value. Right? So in the previous meeting, we talked about MD5, and we talked about SHA-256. Right? So these are all examples of hash functions. So you can place in any input, variable length input, and you run it to the function, and you get a fixed length value for that particular variable length input. Okay. Now the problem is, the idea here is that the hash value should be unique for each input. Right? However, in some instances, collisions can happen, meaning you have different inputs, variable length inputs, and they map to the same hash value. So that's a weakness when it comes to hashing. And in the case of MD5, for example, it's possible to show or to prove that sometimes MD5 collisions can happen. And that will, of course, violate the authenticity. If you can forge something to have the same hash value as the original, then that will be a problem, right? So the next topic is message authentication code, or MAC. So ano itong message authentication code? So the idea here is to append an authentication tag to the plain text. Right? So instead of encrypting the entire message, what we do is to just generate a tag that somehow represents that particular plain text and append that to the plain text message and transmit that over the network. Okay. So that's what we mean by message authentication code. Right? And the question is, why plain text? Right? Well, there are several reasons. One reason is since, for example, if the plain text is not necessarily important, meaning we don't need to guarantee confidentiality, we can just use plain text as is, okay, without encrypting it, and then simply attach the MAC to ensure that it is authentic. For example, we have here the message, we have a MAC algorithm and some key, it will generate this tag, and then you append it to the plain text, transmit that at the receiver end. The receiver will get both the plain text and the tag, and then it will extract the message from the actual message from the concatenation of the plain text and the MAC, and then you run the algorithm. You will get a computed MAC here and compare that with the attached MAC, and if they are the same, then the message is authentic, right? So that's message authentication code. Now, it's also possible, which actually the actual techniques being used, is to generate the message authentication code with hashing. Unlike in this original implementation, wherein the message is actually applied to the MAC algorithm, what happens is that the message is hashed first, right? So the message is hashed first. So, and then and this one also, right? So the message, okay, with some key here, and then it's also hashed first. So this is what we mean by generating a MAC with hashing. So it's actually what is being used nowadays, right? For example, let's take using symmetric encryption. Okay? So the message is hashed. Let's say this can be SHA-256 or MD5. And you get a hash code, a hash value here. And then that hash value, that MAC, will be encrypted with a key that is shared by both this is symmetric, both the sender and the receiver. And you encrypt that and you get this tag. And then you attach that here, and that's what you transmit, right? So you can also use public key encryption, right? Wherein after generating or obtaining the hash value, you encrypt it with the private key. Right? And you get this message and you attach it here, and you send that to the destination, and then you perform the algorithm again. But this time, instead, you don't use the private key because this is not public. So what you do is to use the public key to decrypt this one, and you compare the MAC. If they are the same, they are equal, or that means they are verified authentic, right? So this is actually the concept behind digital signatures. So in a way, you're attaching a signature here. So this form as your signature. We'll have an example later using OpenSSL. Or you can also have a keyed MAC, okay, HMAC, okay. So you have some keys here, and then you append, prepend, append and prepend. Then you pass it to the hash algorithm, you get the MAC, and then you simply place that here. Okay, so yeah, so this is how MAC, generating a MAC with hashing. Now let's talk about public key encryption. So public key encryption is based on mathematical functions and not simply on substitution and transposition of bits. So you recall in the symmetric encryption, wherein you have, basically you have, let's say, block ciphers, right? So it's treated as a block of bits, and then you perform some transformations like substitutions and transpositions on those block of bits to generate the ciphertext. But here in the public key encryption, we don't do that. Rather, we take advantage of mathematical functions and properties and perform the operations based on these mathematical functions and properties. Okay, so essentially what happens here is that if you have a plain text, let's say a string, you have to convert that plain text or string to a number, and then we perform operations on this large number representations of text. Let's say hello world. So hello world will have to be converted to a number before we can perform public key encryption. Okay, so that's why public key encryption is actually slower than secret key encryption because of the mathematical computations involved. Right. So that's one property. Another one is it uses two keys. You have the public key and the private key, which as you've seen earlier. And it's also known as asymmetric encryption. And since there are two keys in this scheme, we need some form of key generation algorithm to generate the public key and the private key. So we have different algorithms for public key encryption. We'll discuss one later when we go to the RSA algorithm or RSA scheme. Now, what are some common misconceptions about asymmetric encryption? Okay, the first one is that it's more secure than symmetric. So it's not guaranteed that it is more secure than symmetric, right? Because the security of the security is basically based on how you break the encryption, for example, by doing brute force attacks or cryptanalysis. Okay, so this does not necessarily mean that public key encryption is more secure than symmetric. The second one, it has made the symmetric obsolete. Oh, we have a new public key encryption scheme, so symmetric is already obsolete. Now, the problem is with that is that there are advantages and disadvantages with both approaches. As I said earlier, symmetric encryption is actually faster compared to public or asymmetric encryption. And easier key distribution. Now, since encryption relies on keys must be distributed to the parties, to the interested parties. So it is also false to assume that the distribution of the key is easier, right? When we go to PKI, for example, okay, the lab on PKI, so we have to make some assurances that the public key is actually from the original entity who claims to own that particular public key. So that's why we have the public key infrastructure for that. So take note of these three misconceptions, because let's say in job interviews, you might be asked, okay, why is asymmetric encryption more secure than symmetry? Does it make symmetric encryption obsolete, or it's easier to distribute the key? Okay. So asymmetric encryption can be used for both confidentiality and authenticity, which we will demonstrate later. So we have two keys. We have the public key and the private key. Now, if we're going to use the asymmetric encryption for confidentiality, this is how it's going to work. You have the plain text and you have the encryption algorithm. Now, on the sender side, this one is Bob. This is the side of Bob, right? Bob maintains what we call a key ring. It's basically a keychain. Right? So you have a keychain that contains the public key of individuals or entities that Bob would like to communicate. So Bob's public key ring or public key chain. Right? Now, if Bob would like to send something to Alice, it has to get this public key from the key ring and then use encryption, the algorithm, let's say RSA, together with the plain text to generate the ciphertext, which will be transmitted to Alice. Now, at the receiver end, Alice will use her private key to decrypt the ciphertext and eventually obtain the plain text. So this is an example of asymmetric encryption for confidentiality. Right? Because it is only Alice who has her private key can decrypt anything that was encrypted with her public key. Right? So that's for confidentiality. Now, for asymmetric encryption for authenticity, this is the reverse, right? Instead of using because we want to guarantee authenticity, we want to ensure that the message that we received actually came from the sender, right? So what happens is, in this case, for authentication, the plain text is encrypted But instead of using since this is Bob sending, would like to tell Alice that this message is from me. Okay, so this one is Alice. Okay, so Bob will encrypt the message, the plain text, with his private key, and then transmit that. And then at the receiver end, the Alice, for example, in this case, will use the public key of Bob, okay, to decrypt this encrypted message and get the plain text. If Alice is able to get the plain text from the ciphertext signed with Bob's private key, this means that this plain text, this ciphertext message came from Bob. Okay, so this is called basically the base for digital signature. What are some applications of asymmetric? So we have digital signature, symmetric key distribution. It can actually be used to distribute secret keys. I did not discuss the Diffie-Hellman key exchange algorithm, but this one is also using mathematical functions and operations to distribute secret keys. Okay, so that's one application. And then encryption of secret keys. So you can use this to send secret keys. Okay, using this mechanism, for example, this RSA. So what are some of the requirements for public key encryption? So the first one, it should be computationally easy to generate key pairs. As I said earlier, there are two keys that must be generated. It's called a key pair, the public key and the private key, denoted in this manner, K sub pub and K sub pre. And easy to encrypt. So it should be the ciphertext can be generated using some function with the public key, for example, and the message M. It should also be easy to decrypt. You can get the plain text or the message by running an algorithm using the private key and the ciphertext obtained here in step 2. It should be infeasible to get the private key from the public key. So most people, or the typical use of asymmetric encryption is to distribute the public key. Right? Now, given the public key, it should be difficult, okay, computationally, in fact, computationally infeasible to get the private key from the public key if you have access to the public key. And it's also infeasible to recover M, computationally infeasible to recover M from the ciphertext and the public key. Okay, so that means that only the private key can recover the message M. And it's also useful if both the keys, public and private, can be used to encrypt and decrypt, as we discussed earlier. Okay. What are some of the examples of asymmetric encryption? So we have RSA, we have Diffie-Hellman, we have the digital signature standard, and the elliptic curve cryptography. Applications include digital signatures, key distribution and management, certificates, okay, which is part of the PKI lab, and the secret key distribution, as well as temporary keys for encryption. Now, in the PKI lab, you're going to look at the public key. We're going to use public key certificate. So, as I mentioned earlier, one of the misconceptions is that it's easier or more secure key distribution when it comes to asymmetric encryption, because you just simply publish your public key and your private key remains private. Nobody can access that, only you. So, but the problem with that is I can claim that when I publish my public key, for example, that others can actually claim that the public key that they release is actually my public key. So there will be some confusion because of that. So they developed this PKI, wherein we have what we call certificates. So what it does is, let's say we have, this is me, this is Bob, for example, and then information about Bob will be placed here, and then the public key of Bob will be placed here also, and there should be some entity called the certificate authority that will attest that indeed this is Bob, the original, the authentic Bob that we're talking about here. So the key here is the certificate authority. Okay, so it's a trusted entity. For example, in UPLB, for example, if we want to implement digital certificates, we can let's say this is my student information, and this is my public key. Then this certificate should be signed by let's say ITC, right? Because ITC maintains the record of students. So we have this certificate authority information, and then the way it is used to verify, right, the authenticity of the public key. So in this case, for example, this information will be passed to a hash function. Okay, so it will be hashed, and then you get a code here, and then you encrypt that with the hash code, encrypt hash code with the certificate authority's private key to form a signature. Okay, so this is the create a signed digital certificate, and then you attach that. So this is the certificate, then you transfer that over the network. So what is the format of that? We have the X509 standard, and then okay, so at the receiver end, this one is also hashed, and then this one is decrypted by the public key of the certificate authority, because the public key should be published by the certificate authority. If, let's say, they are the same, that means that this information is authentic. Okay, so the recipient can verify signature by comparing hash code values. So that's essentially how it's done. So this is used in HTTPS. This mechanism is used in HTTPS. So SSL. So you have a lab for that, which is the PKI lab, to explore further this mechanism, public key certificates. Okay. So we now move on to the RSA algorithm. Right. So this is one of the algorithm, public key encryption algorithm is basically very popular. Okay. So that's why it's called RSA, because it's Rivest Shamir Adelman. It uses the exponentiation of integers modulo a prime number. Right. And it's a block cipher, 128 bytes. You will see later. Plain text and ciphertext are integers between 0 and m 0 and n-1 for some n. Right? So that's the the block size, right, for RSA. And the encryption algorithm is very simple. So you represent the message as an integer m, big integer m, raise that to a value e, some exponent e, and then modulo n. Okay, so that's the ciphertext, and the decrypt operation would involve the ciphertext c raised to d, some value d, mod n. So it's actually called the modulus. Okay, modulus in actual implementation, and can also have this representation to retrieve the actual message. So this RSA technique satisfies the requirements I discussed earlier. So how does this work? At the minimum, the sender and the receiver know n and e. N is the modulus, as I said. So if, let's say, you want to send an encrypted message, okay, you need to know the n and the e, right? Because this is the important parameters here in the encryption. Okay, so m is just the big integer representation of the message, and only the receiver knows d. Okay, only the receiver knows d, because that will be used for decryption. And mathematically, we can represent the public key and the private key as a set. Okay, so a set or a pair. Right, so probably it's better to represent this as a pair. En, okay, not a set, and dn. So this represents the public key, and this represents the private key. Okay, so how does this algorithm work? So I have here, representation on how RSA work, because you need to at least know how it works to be able to solve some problems, or at least know internally how the operation works. So the first step is key generation. Okay, so in key generation, you have to select two prime numbers, P and Q, such that P is not equal to Q. So on the right side, we have an example. Let's select P for 17, Q 11. So these are prime numbers, and they are not equal. Then the next one is we compute N, which is the product of P and Q. So in the case of this, in our example, N is basically 17 times 11, which will give us 187. So this will be our N. Then we compute phi N, right? So phi of N, right? So phi of N, so this phi 187 is just P minus 1 multiplied by Q minus 1. So 17 minus 1, 16, 11 minus 1, 10. So phi 187 is 160. Now we need to select an E such that the GCD, or the greatest common divisor of phi of N and E is equal to 1. So you can do this brute force or exhaustively. Okay, you loop from 1 to phi of N to be able, and then compute the GCD for each value of E that you can get, and then if it equals to 1, then you choose that as the E. So let's say in this example we choose 7, since GCD of 160 and 7 is equal to 1. So E now will be 7. Now we have N and we have E. So that means that we already have our public key. Okay? Next, we select the D parameter. Okay? Select D such that D times E mod phi N is equal to, phi of N is equal to 1. Okay? So we are to find D such that it satisfies this congruence. Okay? So to be able to do that, so we have this notation, D times 7 mod 1, 6. So we're looking for the value of D. So using a modular inverse algorithm, we will be able to obtain D equals 23. So we now have all the information that we need to be able to perform RSA. We have N, we have E, and we have D. So we can have this public key and private key. So public key will be 7, 1. Let's just use a pair here. Okay, so that we have consistent notation. And this will be our combination of public and private key. To perform the encryption, let's say our message is M is represented by 88. Then the ciphertext will be 88 raised to E, which is 7, modulo 187, which is the N modulus, and we get 11. So this will be our ciphertext. Now we're going to decrypt this using the private key. This will be the notation M equals the ciphertext is 11 raised to D, and then modulo 187, and we get 88, which is the original plain text or the original message. So very easy to do, right? So that is how RSA works, right? So the inventors really are very creative, right? Very smart to be able to do this. And of course, the security is based on the size of the keys, right? So the higher the number of bits, let's say 2048, 4096, the harder it is to perform factorization in order to be able to derive the parameters for this encryption scheme. Okay, so that's an example computation, hand computation for RSA. Okay, so in the lab, as I mentioned in our Slack, okay, we're going to provide a solution to task 3 in the RSA lab. Okay, so what is this RSA lab? Okay, so Let's look at this one. Okay, so this is the RSA lab in the seed lab. Okay, this is the path. Okay, so task 3, so in order to perform RSA, okay, programmatically, you need to learn what we call the Big Num API. Right? So basically, it provides an API to be able to compute operations for very large numbers. As you may recall, in computers, let's say if you have a 64-bit integer, for example, or 1 to 8-bit float, okay, there's still a limitation, okay, on what you can do on the size, right? So they usually implemented this Big Num APIs, which actually provides some functions to perform operations on big numbers. So this is part of the OpenSSL library, and in this lab you have some example code and some description of the functions that you can use. But you can of course go to the man page. Okay, let's say man bn deck to big number. Okay, so you get a lot of functions, okay, that are related to big number API. Now, in task 3 that is being discussed here, or that we are asked to solve, to perform, we are to decrypt a message, right? So what we are given here are parameters for that we need to decrypt, like the ciphertext. So we are given the ciphertext here, which is actually a hex string, right? This is the hex string, and then the parameters. It says that use the parameters in task 2. So these are the parameters. This is task 2. Okay, this is task 2, and these are the parameters. So we have n, which is the modulus. We have E, which is the exponent. This is 65537, which is basically this that is being used by OpenSSL. And then this is the message. So our goal is to find this secret message. So our parameters are N, E, and D, right? So can we decrypt this message if we are given these parameters? Okay, so I have here an implementation or a solution to that problem. So you can get this from the this is just one of my gists. Okay, so you can take a look at this URL, a gist, and then go to my account, and you see the RSA computation here to illustrate this. But here is the code. So what do we need? Okay. First, we need to encode those hexadecimal strings, turn them into big numbers. And we have this. First, we create a context. This is the context. And then this one here, this line, will convert the hex string, this hex string, to n, which is the modulus. So here, so we simply copy this one. So this is n. So A5, ang dulo niya. Makikita niyo dito na A5 yung dulo niya. So this is how we convert that to big number. And then this is the 655. This is 65535. I don't know how they use it, but this is, it says here, this is the hex, this hex value equals to decimal 65537. So we just paste that here. So 0001. So this is the hex value. And then we have the D, the value for D. So this is the D. Okay. So 0D. And this one. Okay. And then we have to place in the ciphertext that something that we're trying to crack. So this is the ciphertext HC493F, and you see that here 493F. And then we perform the decryption. Okay, so I wrote a function here, decrypt. So what is this decrypt function? It's basically just an implementation of the formula that I described earlier, wherein you have the message, we have the ciphertext, we have D, and we have N. Okay, so and we use the mod exp. What is this mod exp? If you look at the lab, you'll have this one here, right? So we use this formula, right? We use this function. So this is the M, the ciphertext raised to D mod N, and then the context, and the result will be stored in res, and we simply return M. Okay, so here we create first the return value, the plain text, and then what we do is to decode that. Okay, decode that to the hex string. You're going to get a hex string for M. Okay, and then you can decode that to get the actual plain text. Okay, so this one here is a utility function to convert a hex string to an actual text. Okay, so we can try this. Let's say GCC -O RSA task 3 elf, and then task 3 RSA task 3 C -L crypto, and should get the executable RSA task 3.elf. So this is the actual message in decimal, okay? And then this is the decoded, maybe I can change this. So I have the function here, print bn. So if I want to convert it to hex, okay, this will be the hex value. So this is actually the hex value, and this is the actual text for this particular for the ciphertext in task 3. Okay, so this means that this value is actually password is DES. Okay, so why am I discussing this in this meeting? Because you might have a problem in the CTF that will require you to decrypt a ciphertext in this manner. Okay, so at least you know how to do it. Okay, so next one is RSA in OpenSSL. So we just run through this. So how do we use, in the previous lab, you use OpenSSL for symmetric encryption. You try out different algorithm like AES and try different cipher modes like CBC, ECB, etc. So how do you use RSA in the same manner? So the first step is to generate keys. Okay, so again, the public key systems would require you to generate a pair of keys, a private key and a public key. So this is the command that you're going to use to generate the keys. So we have first you have to call the gen RSA, and then you specify the out file, which is the hacker.pm, and this is the size of the keys. Right? So 1024 bits can be 2048, okay, 4096. Okay, the higher the better. Now this key is not encrypted. You can actually specify an encryption algorithm, let's say AES 128, to encrypt the key. But in this example, I did not place this one so that the key will be presented as is. Okay, and then it will do some, okay, after typing this command, you get some random string similar to the one you did in GPG, in ComSci 137. And you will notice something here that E is 65537, which is actually what we used earlier in the task 3. Right? And what we do is to display the contents of this key file, and you will notice that we have 887 bytes. And if we display the first line of hacker.pm, so it says begin RSA private key. Now the next step is, so it will generate a single file that contains both the private key and the public key. How are we going to extract to separate these two, right? So first we need to extract the public key. So we use OpenSSL and then RSA command, and then our input will be the generated key file, and then the output format will be PEM. So we have different formats for keys, but in this example we use PEM, and then we want to extract the public key, pub out, and then the output file name for the public key will be public.pem. So it will generate the RSA key, and then for the private key, this is how we're going to do it. So out for PM. So we just exclude this option and to get the PM. And then we now have the PM for the original PM. Then you have the private PM and the public PM. So notice that they are integrated. Okay? Almost they're the same actually, the hacker.pm and the private PM. But the public key is contained in the private PM file. So this is the public key. Then we perform ahead. So we get this private key and the public. So this tells us that we were able to obtain, to separate the private key and the public key in this manner, right? So now we have a private key and public key. So remember that for the public key, in our notation earlier, key pub is a pair, not braces. So it's a pair E and N, right? So E is the exponent here, this one, right? And N is the modulus. So how do we view that? By using RSA command. So this is the command, OpenSSL RSA public key in, and then it's the public key. Then text, no out and modulus. So this is basically the N. So notice that it's a long sequence. And if you want the corresponding hex string for that, this is what what you're going to get. Okay. And this is the exponent. So this is E and this is N. So those are the things needed, okay? The parameters for the public key. So there, how do we use this now to do the encryption? So we're going to use, remember that we can use for encryption, we can use both the public key or the private key. So here we're going to use the public key, right? So we have a plain text message secret, and then we display that. And then we use this command RSA utility, input the plain text, this one. Then the output will be the cipher bin. And then we need to specify we're going to use the public key. And then the in key will be the public PM, which we extracted earlier. And then we perform encryption. And after this command, you get this cipher bin. So notice that this is 128 bytes. Okay, so this is the size, the block size for RSA, because we have this a short string to encrypt, right? And then, so this is a binary, so you can use XXD to dump its contents, and this is what we'll get. Then, if you want to decrypt, right, this, you can use RSA util again. This time, the input will be the ciphertext, and then the output file will be the decrypted text. Then the in key, notice here, the in key will be the private.pem, and then we perform the decryption, and we get the plain text. So that's how it does. So we use the public key for encryption and the private key for decryption. Now we can also use signing, the opposite, as we discussed earlier in the figure about using the private key for encryption. This is how it's done. So again, we created the message, and then we use RSA utility. In key will be the private, the PM, the private key, and then we use the plain text, and then the output will be the cipher bit. And then instead of using encrypt, we're going to use sign, right? Signature. And then we'll get this output again, right? And then we have the binary file, And then if you want to check for authenticity, okay, RSA util, we're going to use the public key. So pub in key, we use the public key, and then out decrypted.txt, and then the opposite of sign is verify. So I failed to specify the input file, which is cipher.bin, which is the ciphertext. And then when we cut out the decrypted text, we get the secret. So here, in the signing process, we use the private key to encrypt, and we use the public key to decrypt. Okay? And lastly, for this session, we can also use the actual signing routines, okay, which is basically for digital signature called the DGST. So recall our discussion earlier about this one here, okay? Okay. So this one, we're using a public key encryption, right? So we have the original message, and then we pass that to a hash function. This hash function will be encrypted with the private key, and this will be served as a signature, and it will be attached to the message. So that's how is this done in OpenSSL? Okay, so is this signing? So again, we have the plain text, the message here, by secret. And then here we use digest, right? And this is the hash algorithm that we're going to use, right? The hash function earlier. And then we use sign, and then the private key. And then the output will be the mac.bin. So the message authentication code, or the signature basically. And then the input will be the plain text. So we sign this plain text with our private key, and the output, the signature file will be in mac.bin. And this is what we're going to get. And then if we xxd mac.bin, you get this, okay? And then OpenSSL is the opposite process. So verify, right? So the opposite of sign is verify. So we have the digest of SHA-256, and then verify, we use the public key, and then the signature will be mac.bin, this one, and then the plain text, and then should get a verified okay if the contents match. So we're able to verify. So notice that in this one, in this example, without the actual signing, there's no hashing that was done on the plain text, right? There was no hashing done on the plain text. Unlike this one, we have a hashing, which is SHA-256. Okay, so that will be the end for this lecture. See you next meeting. Stop.